Hi again. This video will talk about using Mathematica to create additional constructions in two-dimensional space. These constructions are ones that will generalize to 3D in an upcoming tutorial. First step, let's say we'd like to plot a function of one variable, y equals x squared. This is one of the first things you might want to do with a function. You can use the plot command. Here's the example when we have the function x to the fourth minus 6x squared. The structure of this command is you put the function, so y equals, you don't put the y equals, but you put the right hand side of that equation, and then you tell Mathematica the domain of x values that you want to plot. When you do this, you get a Mathematica determined function where it tries to give a picture of the whole range of the function over that domain. You may be interested in restricting the x values, so to restrict the y values. So to restrict the y values in a plot, you can use the option where you specify what the plot range is. Here we've restricted this to go from -10 to 10. And if you don't want any axes, or if you want to change the color of your plot, you can use plot style to change color, or add some dashes, etc. And you can turn the axes option to be false, and that gets rid of those axes. Alright, so that's a simple thing for using Mathematica to plot functions from R to R. You can also use Mathematica to plot parametric curves. So remember that a parametric curve, parametric function, is where both the x-coordinate and the y-coordinate of the function are defined as a function of an independent variable, often using t, where you think of t as the time, and then you figure out what x is as a function of t and y as a function of t independently. So when you have a function that is a parametric function and you'd like to see what the curve is, you use parametric plot. So one of the simplest examples in a parametric function is you can draw the unit circle by writing the points of the form cosine of x comma sine of x as x goes from 0 to 2 pi. So the structure of this command is you type in parametric plot, you use your braces for the x function and then the y function and brace, and again this this variable, the independent variable, you say what the domain of that variable is. And so when we do this, we get our circle. This variable doesn't have to be x, often it would be t. A nice modification of this type of function is gives the Lissajous curves. So here we've taken our cosine of x and replaced it by cosine of 5x, our sine of x replaced it by sine of 3x, and basically what happens is here in cosine of x and sine of x, the point goes from 1 to -1 to 1 in 2 pi time, and the sine goes from 0 to 1 to 0 to -1 back to 0, and so that makes the circle. By putting a coefficient here, that's basically speeding it up. Instead of going from 1 to -1 to 1, it goes 1 to -1 to 1 to -1 to 1 to -1, a total of 5 times. So that's going to give us this pattern here, and we can put a whole bunch of these curves in a table format using a table command. So here's a whole bunch of different Lissajous curves. I think they look pretty cool. Here's one last fun example involving parametric curves. You can use parametric curves to make almost any type of shape. Here, if you go into Wolfram Alpha, you can search for things like the Homer-Simpson curve, and this has been created as a function, as a parametric function, where basically you're following along with an approximation to these shapes as a function of time. And so you've got one curve as a function of time, and then you started another curve as a function of time, and you just keep putting in these bits one at a time, and you can create this curve. So it's not like it's y equals x squared. The actual function is this. You've got a whole bunch of bits. Each one of these represents one of the curves that you see in the picture. So it takes a little bit more time to create something like that than using a mathematical function. All right, let's head over to another example of a one-dimensional output that you might get using Mathematica. Let's say you have some points and you'd like to get a curve that approximates those points. So to do that, you can use a B-spline curve command. And when you do that, it takes in the points and gives out a curve that is determined by those points. So it's called a non-uniform rational B-spline curve, and the points are the control points. So here's some points. Let's see what they look like. So these points look like this. Kind of hard to see. Let's make them a little bit bigger. Point size 0.1. Let's see what happens with that. There we are. So that's what these points look like. And so what we'd like is we'd like a curve that starts out at this first point, kind of follows these points, and ends at this point. So let's also add in, so let's make these a little bit smaller again, and let's add in the lines that visit those points. So this is the lines that follow those points. And so let's see what happens with the B-spline curve. What the B-spline curve does is you can see it's using those points to make the shape of this curve. One thing you can do to take this curve and make it into a closed curve is to specify that you want a curve where the spline is closed. And when you do this, it then adds in one more point that connects this one back to this one. If you'd like to really ensure that your spline passes through the points that you've specified, you can go in the documentation center. There's an example where you can actually get those points. Another option is to use interpolation. But what I'd really like to show you is how you can take this curve and then turn it into basically a polygon of that shape. All right, so there's two parts to this. The first part is that we're going to take this curve right now is a graphics primitive by itself. It's just this curve. And what we're going to do is we're going to turn this curve into a function by changing this B-spline curve part to be a B-spline function. And so what that's doing is it's taking this curve, and now it replaces that by a parametric function, just like we had above, where the parametric function starts at 0 and goes to 1 and follows the whole curve during that time frame. So this is something we're going to do in 3 dimensions too, when we want to take a a one-dimensional path in 3 dimensions and put a tube around it so that it's in 3 dimensions and not one. So what did we do? Let's just go back and recap what we did. Here was the code for creating a spline curve, and what we did is we just changed that. We changed it from B-spline curve to B-spline function. This is now a function. It takes as an input the time variable, which goes from 0 to 1. So if we do a parametric plot of this, then we have a curve that the curve of the graph of the function follows that same outline. Okay, so that's part number 1. The second part uses some advanced mesh capabilities of Mathematica. We're going to talk about that in a future tutorial, but let's evaluate this code. We're going to use boundary discretized graphics, and what that's going to do is basically take a lot of little points along the way and use them as the boundary of a shape. I don't know if we can see that if we zoom in enough. There are options where you could make this, you could end up seeing the lines, but here the resolution looks pretty good. So now what we have is we have this region, and in Mathematica 12 you can take this region and use it just like you would a polygon. And so we can take this region, say that we want the edge to be black and thick, and that the inside to be magenta, and this works just like you would use a polygon. So this is a method by which you can make polygons and shapes that are more complicated than just by defining what the corners, the vertices are of your polygon. Alright, last thing for today is that there's another way to get a two-dimensional output, and that's called region plot. And so the way that region plot works is that you specify some rules, and Mathematica will find all points that satisfy those rules. So let me give you an example. Here's an example where we say, I'd like all points of the form x comma y, where x squared plus y squared is less than or equal to 1. Alright, if we think carefully, what does that mean? That's basically specifying a disk, because we want all points that are within distance 1 of the origin. And so what's the syntax here? The syntax here is, here's the rule. We want all points x and y satisfying some rule. And here are 2 additional things where we specify what values of x do we want to test and what values of y do we want to test. So this is giving us the set of all points between -1 and 1 x's, and the y's between -1 and 1 that satisfy x squared plus y squared is less than or equal to 1. The nice thing about region plot is it lets you use operators to do operations on regions. So you can use the AND operator or the OR operator. Let's see that in action. So here is the function y is greater than or equal to x squared. Well, I guess we would say the function is y is equal to x squared, and then this bowl-like region are all the points that satisfy y is greater than or equal to x squared. Similarly, here's a region where the x values are between -0.5 and +0.5. And so that's going to be this rectangle here. So if we do the first, we want points that are both greater than or equal to y greater than or equal to x squared, and that satisfy the points between x between -0.5 and 5. That's going to create the intersection of these 2 regions, because all the points in here are both in here and in the rectangle. On the other hand, if we said, I want all points that are in this region, the bowl region, or the rectangle region, that's going to give us the union of those two shapes. So region plot is very helpful when you want to define, when your points and regions that you want to define are based on inequalities, or if they're based on doing intersections or unions of regions. All right, that's all for today. Let me put this last note here in the tutorial. And take care. See you next time.